Equipment Lesson 7 is Quality Control Testing, 15 minutes and one of the highest yield advanced lessons in the equipment operation category. Quality control is how a department confirms that every piece of imaging equipment is performing within established tolerances, protecting patients from unnecessary dose and ensuring every image meets diagnostic standards. We cover the QC program structure, KVP accuracy, timer accuracy, HVL, beam restriction and light field alignment, digital receptor QC for both CR and DR systems, reproducibility and linearity, reject analysis, fluoroscopy equipment, QC, display monitor standards, and the complete QC testing schedule. Let's get into it. For foundational QC concepts. Why QC exists. The goal is to confirm that X-ray equipment performs within established tolerances, protecting patients from unnecessary dose, ensuring diagnostic image quality, and satisfying regulatory requirements from the ACR, the Joint Commission, the FDA, and state radiation programs. Equipment drifts over time. Without QC, that drift is invisible until it causes patient harm or diagnostic failure. The two-part program structure. Quality control, QC, is the technical testing of equipment performance. Quality assurance, QA, is the broader program that includes QC, plus policies, training, documentation, and all other quality-related activities. QC is part of QA. QA includes everything. Roles and responsibilities. The medical physicist performs acceptance testing, the annual equipment survey, shielding calculations, and the bar chart on this slide shows a KVP accuracy test. Set KVP values on the x-axis, measured values shown in orange bars, and the ideal values in dark bars. In a properly calibrated system, the two bars track closely at every station. Deviations beyond plus or minus 4 kVp require calibration before further clinical use. KVP accuracy. Tolerance, within plus or minus 4 kVp of the indicated value at every station. Test tool, A non-invasive KVP meter placed in the beam. Frequency. Acceptance testing and annually. If outside tolerance. Remove from service, calibrate before returning. Timer accuracy. Tolerance, within plus or minus 5% of the set time across the full range of clinical timers. Test tool, a synchronous motor spinning top for single phase. Units, a digital timer test device for electronic timers. Frequency, acceptance testing and annually. Electronic timers rarely drift on their own, check after any repair. To timing circuits. MA linearity. Tolerance, the line chart on this slide shows beam intensity falling as aluminum thickness increases. The point where intensity reaches 50% of the original value is the HVL. The half-value layer, measured in millimeters of aluminum. HVL definition, the thickness of aluminum that reduces beam intensity by exactly 50%. At 80 kVp, the HVL is typically 3.0 to 3.5 millimeters aluminum. Equivalent in a properly filtered beam. Why HVL matters. Low HVL means inadequate filtration. Too many low-energy photons remaining in the beam, those photons are absorbed almost entirely in the patient's skin. Adding dose without contributing to the image. The NCRP mandates minimum HVL values for every operating voltage range. Below 70 kVp, 1.5 mm aluminum equivalent. Above 70 kVp, minimum total filtration of 2.5 mm. Aluminum equivalent, which produces a corresponding minimum HVL. How to measure it? A calibrated ionization chamber plus aluminum attenuators of known thickness. Light field and X-ray field congruence testing. Purpose: confirm that the visible light field projected by the collimator accurately matches the actual X-ray beam area. If they don't match, every positioning decision based on the light field is wrong. Method: place radiopaque markers, pennies work well, at all four corners of the light field. Expose, develop or display the image. Measure the difference between the marker positions and the actual beam edge. Tolerance: the sum of all misalignments must not exceed 2% of the SID in each dimension. At 40-inch SID, maximum discrepancy equals 0.8 inches, or 2 centimeters, per dimension. Frequency: acceptance testing, annually, and after any collimator service or repair. Failure: remove the unit from service. Every exam taken with a misaligned light field has been centered inaccurately. Positive beam limitation, PBL, testing. Verify that autocollimation restricts the field to the image receptor size at every tested SID and receptor size combination. The field must not exceed the receptor size by more than 3% of SID, required for all fixed radiographic units since 1974 per FDA regulation. 6 digital receptor QC tests, for apply to both CR and DR, 2 are specific to each system. Flat field uniformity, DR only. Expose the detector with no patient or phantom in the beam. The entire image should display uniform brightness. Non-uniformity, bright or dark areas, indicates dead detector elements or gain calibration. Drift frequency, daily in high-use rooms, weekly minimum. Spatial resolution. Expose a bar pattern resolution target. Measure resolving capability in line pairs per millimeter. Compare to baseline established at acceptance testing. Degradation indicates detector element failure or phosphor aging. Exposure index calibration. Verify that the EI produced for a known phantom exposure matches the expected value. Ensures EI numbers are accurate for dose tracking and deviation index monitoring. Part of acceptance testing. An annual QC. Erasure adequacy, CR only. Expose a PSP plate to a high-dose image. Erase it. Then expose a flat field image. No ghost of the prior exposure should be visible. Ghost image equals incomplete erasure equals prior exam data. Contaminating the next study. Artifact evaluation. Inspect each QC image for unexpected artifacts. Document type. The bar chart on this slide shows MA linearity testing. Expected MAS output in dark bars and measured output in orange bars across 5 MA stations. In a well-calibrated system, the bars track closely. A station showing significantly higher or lower output than the others fails the linearity test. Reproducibility. Same technique settings, multiple exposures. MAS output should vary by less than 5%, a coefficient of variation of 0.05 or less. Poor reproducibility. Means inconsistent image quality and unpredictable patient dose. MA linearity. Output in milliroentgens per MAS must stay within plus or minus 10% between all MA stations. Tests that dose scales predictably as MA changes. Radiation output. Measured output in milliroentgens per MAS must be within plus or minus 10% of the calibrated reference value. Focal spot size. Measured by star pattern test, pinhole camera, or slit camera. Per NEMA standards, focal spots up to 1.5 mm can be up to 50% larger than nominal, above 1.5 mm can be up to 40% larger. Collimator accuracy. Field size at indicated SID within plus or minus 2% of SID. All 5, tested at acceptance testing and annual. Reject analysis is one of the most clinically practical QA tools, and one of the most commonly tested on the ARRT. Track all repeated radiographic exposures. Record the body part, projection, reason for the repeat, and the technologist who performed it. Acceptable repeat rate in most accreditation standards, 5 to 8% or less. Categorize every repeat by cause. Exposure error, too light or too dark. Positioning error, anatomy cut off or incorrect. Projection. Patient motion. Equipment failure. Or patient factors, patient unable to cooperate. Each category points to a different corrective action. Monthly trend analysis. Is the repeat rate rising overall? Is one body part consistently high? Is one technologist consistently higher than others? A systematic problem is not solved by blaming individuals, it is solved by identifying the root cause and addressing it systematically. Corrective action must be documented and followed up. Additional QA program monitoring elements you need to know. Sensitometry 4. Film processor QC, speed, contrast, for fluoroscopy QC. Requirements with direct registry relevance. Maximum entrance dose rate. FDA limit, 88 mg per minute entrance air Kerma rate in standard mode. Fluoroscopic units must be tested to confirm they do not exceed this limit. High dose mode requires separate verification that it can only be manually activated, not the system default. Last image hold function. Verify that LIH displays the last acquired image after the beam is off. Test that LIH is clearly distinguishable from live fluoroscopy on the monitor. LIH is the single most dose-reducing feature in fluoroscopy and it must function correctly. Image intensifier or flat panel detector QC, spatial resolution tested with a resolution test pattern. Contrast tested with low contrast inserts in a standard phantom. Distortion tested with a grid pattern, pincushion distortion measured in image. Intensifier systems. Quantum noise and dynamic range assessed. Automatic brightness control, ABC, testing. Expose a phantom of varying thickness. Image brightness should remain consistent as thickness changes. ABC should not allow dose rate to exceed FDA limits even at maximum phantom thickness. Display monitor QC, the complete QC schedule across all time intervals. The registry tests individual test frequencies directly. Daily, performed by the technologist, flat field uniformity. For DR systems, artifact check, monitor visual QC, and current reject rate review. CR erasure check. These are the eyes on the equipment checks that catch problems before they affect patient care. Weekly, technologist, exposure index trending, sensitometry for any film systems. Still in use, darkroom fog if applicable, and processor QC. For film chemistry. Monthly, technologist and QA officer, full reject and repeat analysis, trend review, corrective action follow-up. And protocol compliance audit. Semi-annual, technologist and physicist collaboration. Spatial resolution, SNR and CNR, exposure index. Calibration, focal spot check, and collimator accuracy. Annual, medical physicist, KVP accuracy, timer accuracy. MA linearity, HVL measurement, full radiation output. Complete fluoroscopy QC, display monitor physics testing, and shielding survey. Acceptance testing, medical physicist only, complete. Baseline testing of all parameters before the unit enters. Clinical use. Establishes every reference value used for. Comparison in all future QC testing. After repair, all 3 QC questions in the ARRT format. Think before. The answer appears. The answer is C. Remove the unit from clinical service and arrange KVP calibration. At 80 kVp, a measured value of 86 kVp represents a plus 6 kVp discrepancy. Outside the plus or minus 4 kVp tolerance. Any equipment that fails a QC test must be removed from clinical service until corrected and retested. Continuing. To use an out-of-tolerance unit exposes patients to inconsistent and unvalidated doses. Adjusting technique to compensate is not acceptable, calibrate the equipment. The answer is D, 2.5 mm aluminum equivalent. The NCRP requires minimum total filtration of 2.5 mm aluminum equivalent for diagnostic X-ray tubes. Operating above 70 kVp. This is measured as beam quality by the HVL, confirmed during annual physicist testing. Total filtration includes inherent filtration from the tube. Typically 0.5 to 1.0 mm, plus added filtration at the tube port. Inadequate filtration means excess low-energy photons, absorbed in the patient's skin, adding dose without contributing to the image. The answer is B. Review technique charts and verify AEC. Chamber selection for lumbar spine. A 12% repeat rate is well above the acceptable 5 to 8% threshold. And exposure error, as the primary category, points to a systematic technique or AEC setup problem, not random error. Before adjusting technique blindly, identify the root cause. The most common exposure error on AEC lumbar spine is incorrect chamber selection, using lateral chambers when the center chamber is required. Review charts, verify chamber identification, and educate staff before making any blanket technique changes. You covered the QC program structure, KVP and timer. Accuracy with the test chart, HVL measurement and the NCRP filtration minimum, light field alignment testing. With tolerance calculations, digital receptor QC for both CR and DR, reproducibility and linearity with the output. Chart, reject and repeat analysis, fluoroscopy equipment QC, DSOM display monitor standards, and the complete testing frequency schedule. QC is how you protect every patient, including the ones whose images you will never personally review.